Good afternoon, everyone. I'm Hao Huang, Assistant Professor of Social Sciences, and welcome to the Illinois Tech Social Sciences Great Problems, Great Minds seminar series. For this seminar series, you can submit questions during the webinar by typing in the chat box. We will open the floor to your questions at the end of the webinar. Now I will introduce today's speaker, Dr. Quynh. Dr. Quynh is our Associate Professor of Epidemiology and Biostatistics in the School of Public Health at the University of Maryland. She holds a PhD and MSPH in epidemiology from the University of North Carolina at Chapel Hill, and a bachelor degree in human biology from Stanford University. She's a social epidemiologist focusing on contextual and economic factors as they relate to health. She has extensive experience using numerous national and international population-based health services to examine social and economic predictors of health and to quantify national and international patterns in health disparities. Her current research program focuses on creating and validating neighborhood indicators constructed from non-traditional big data sources such as social media data and Google Street View images. Her research has been funded by National Library of Medicine and NIH. She was the principal investigator of our K01 Career Development Grant through the Big Data to Knowledge Initiative, and an R01 grant from the National Library of Medicine to pursue this research program. Dr. Nguyen is also currently the principal investigator of another data science-driven R01 grant from the National Institute on Minority Health and Health Disparities to construct an AI-powered chatbot to deliver health information to racial, ethnic minority groups. So it's very delightful to welcome Dr. Nguyen.
Oh, wow. Thank you so much for the kind introduction and the invitation to present. I'm very happy to present and so fortunate that you are interested in this work. I'm going to try to be pretty fast through my presentation. I have a lot of slides, but I actually don't mind it if you ask questions. Like, I know that we generally leave questions to the end, but I don't mind it if you have questions during the presentation as well. I'd rather have a discussion. So I'm going to go through this project. Has been going on for 5 years. It was my first R01, and we're actually in year 5, so it's a nice opportunity to look back at what we've done. Okay, so I will proceed. Let's see. I'm going to. Oh, I'm having. Let's see if I might have to restart my presentation. Okay. And then move. Apologies, I'm going to move things over a little bit. Okay. Okay. So for those who don't know much about Google Street View, because it's kind of a more non-traditional data set, especially for public health and social sciences. Google Street View is collected typically by cars, Google cars driving down roads with special cameras mounted on the top of the cars. So the cars will capture overlapping images and try to construct a 360 view of the environment. One thing that is good to keep in mind, and is both a strength and limitation, is that Google does update the image on a frequent basis for urban areas. So for instance, Washington, D.C., New York City, and those like densely populated areas will get basically yearly or more than once a year update. But for less dense areas, the frequency of updates is lower, and it is also dependent on weather conditions. So the first paper that we did was actually the pilot for this R1 grant, and it focused on 3 cities: Salt Lake City, Utah, Chicago, Illinois, and Charleston, West Virginia. And it was trying to demonstrate the feasibility of using computer vision to examine built environment characteristics from Google Street View. Previous to our project, people had started to use Google Street View, but more in the sense of manual annotations. So you started to see platforms being built where you can have like your research staff annotate the images, but then that was done manually. And you can kind of, the scale of which you can understand neighborhood environments is going to be limited by the manual annotation. So we wanted to automate it by using computer vision, but we had to demonstrate whether that's going to be possible. So we downloaded images from using Google Street View API for these 3 cities. To do so, we actually collaborated with Dapeng, who presented during the semester, and we selected images on a down road networks. So that each sample point was around 50 meters apart. So we went down the road and sampled images along the road just to make sure that we were comprehensively examining the environment. And then each location we sampled four points from the west, east, north, and south. So in total, we sampled over 200,000 images from Chicago, under 50,000 from Salt Lake, and 53,000 from Charleston. And the image varied because the road networks vary, with more road networks being in Chicago, and then that means more opportunities to sample images. Okay, so we started with 3 indicators. People always ask, why do we select these indicators compared to any other indicators? It was based upon a feedback loop between feasibility of the computer vision model as well as importance to the neighborhood research realm. So things like walkability, neighborhood disorder, and urban development are key features of a neighborhood, and they have long-standing literatures about their impacts on health. So that we selected crosswalk as an indicator of walkability, building type as an indicator of mixed land use. We noticed, for instance, in the Google Street View images, there were neighborhoods where they just had all single family detached homes, and then compared to other areas that had like a mixture of apartments, grocery stores, and then homes. So when an image had a building other than single family home, then that indicator was the second one, where it was like not single family home was indicated. And then street greenness, because there's a pretty robust literature about how.
Sorry to interrupt you.
Yes,
It seems your slides is become not a full screen.
Oh, yes. Okay. Oh, yeah. I have my notes there, but I can.
Oh, okay.
Yeah.
Okay.
Yeah. But I think this might be better because it's going to be bigger if I make it into a full screen. Yeah.
Oh, okay.
That's my notes. So it's
okay. Okay. Yeah.
And so the last feature is street greenness. And that is just being a street greenness is generally tied to more physical activity. People generally like to walk and have physical activity in places that are greener. So that encourages walking, and green space is also associated with less mental distress. So we kind of selected these 3 indicators. So we manually labeled images, first from Chicago, but then just testing the models, we realized the models were not performing well in Charleston. So we added 2,000 manually labeled images from Chicago to boost the accuracy, because rural areas look different from urban areas, and the model needs to kind of have more of that heterogeneity. So inter-rater reliability, when you're manually labeling images, we made sure that agreement between raters was above 85%. When you have a labeled test, when you have a labeled set of images, we dedicated 80% to serve as a training set for the computer vision models, and then 20% to serve as a test set. So the test set is just to evaluate how well the model is performing. And so generally these models perform pretty well with accuracies above 85%, and then crosswalk was the best at 93%. So it just demonstrates that for these features, the computer vision model can detect them and label them with pretty good speed at the image level. And these are just some example pictures to give you an idea of what the how the labels would manifest. So here, green 30 would be indicated by 1, saying that feature is present, because we have a lot of trees here, we have grass. So green 30 is just like the approximation of like, does 30% of the image have like greenery? And that cut point was selected because we noticed almost all images have some greenery, like in terms of a tree or a little bit of a lawn, but we wanted to separate between pictures that had a lot of that compared to just very little. And here we have a crosswalk present, and then we have non-single family home present, which is in like the buildings to the left and right. Those are like bigger than typical non-single family detached homes. Oh. I noticed if I'm in the full screen, it doesn't click forward somehow. It gets stuck. I don't know why. Oh, okay. Okay. There. And these are just some additional features. So green 30 was also is accurate even if the leaves are not present on the trees. So here you all the leaves have fallen down, and that's because we have training data where we label winter scenes. So as long as you provide that information to the model, it's able to still identify greenery or trees, even if they don't have leaves, if you include that in your label data. So this is just like some descriptive statistics about the 3 cities in terms of the characteristics of the neighborhood. So we have Salt Lake, Chicago, and Charleston. Green streets are most present in Charleston. Sidewalks are most present in Chicago, and also not single family home is most present in Chicago. Oh, sorry, it always gets sticky. Okay, so these are just the maps where you can create from the summary data, you can create maps to kind of display the distribution of your neighborhood characteristics. And then below is just some sample images from that area. So this is Salt Lake. You notice that the streets are very wide and clean, and the mountains in the back. And then you can kind of look at the distribution of like demographics, economics with your built environment. So for at least these 3 cities, you had higher income associated with more green streets and less mixed land use. And then we looked at the relationship between these built environment characteristics and health. We see that, for instance, green streets was associated with much lower obesity and diabetes, as well as crosswalks and not single family home. So these were basically protective against diabetes and obesity, because all these 3 indicators in the literature are tied to more physical activity. So next we looked at Google's computer vision API. So the first study was using computer vision models that we implemented. The second study tried out Google's computer vision API. So it was their algorithms, and we just wanted to see what was possible. So we downloaded Google Images again, but this time 16 million from across the US instead of just at those 3 cities. We used the Google's computer vision API to label each image, so each of the 16 million images. And then we examined health outcomes. I would say as a cost, it was kind of expensive. So we actually had cloud credits from NIH, I think totaling 40,000. And I think we used like most of it, like 30,000, to run this computer vision API on the 60 million images. So just in terms of cost, that's what it would take just to run implement this analysis. So this is just one of the features that API could extract is the presence of highways. And when you're working with an API, you always have to like balance between your own research objectives and what the API or the computer vision algorithm could do. So there weren't many that we noticed that we were pretty restricted to features that were very large. The smaller features that they had available had a very low accuracies, like in the 20s and 30%. So that wasn't really, possible for research standards. So we picked large features that had much higher accuracies, but then they have to be very large. So highways is one feature and rural areas is another feature. And this is run across all 60 million images across the US. So this is a comparison between the different indicators of urban rurality, because people say, like, why potentially use Google Street View if there are other indicators, right, of urban development. So on top, we have the Google Street View derived characteristic, and we have outcomes like, obesity, diabetes, physical distress, mental distress, physical inactivity, binge drinking, limited access to food, and dental care. We see that being in a more rural area, as indicated by Google Street View images, was associated with higher chronic conditions, higher mental distress, more limited access to healthy food and dental care. For census-derived measures, so typically that's like something like population density, we see similar patterns, but the beta, the effect estimate, is smaller in magnitude. Some people also use rural urban continuum codes. So you might see that in the literature too. So that's why we test it out. But again, it also has smaller estimates. So we think that there is value in using Google Street View derived characteristics because they're particularly emphasizing the built environment and not like a proxy like population density. Or the rural continuum codes is also good, but it's also updated not very frequently. Like it could be like a 10-year lag. Okay, so additional exploration of computer vision models. So with time, we added more neighborhood features. If you're implementing this at a university, for instance, our collaborators, they use a 1 GPU for training, and then they use like 4 to speed up the data processing. So releasing, making inferences on like millions and millions of images. Okay, this is for people who, sorry. So for people who implement computer vision models, this is the schematics. So you have the input layer, you have the convolutional neural network, you have some classification predicted, and you have error assessment. And these are some more images along with their labels. So this is like a new feature is a single lane, whether it's a single lane road or multi-lane road, and visible utility wires overhead, which is here. Okay. Another dissertation was conducted. So on this project, we had several engineering students come through our lab. And so this one was just looking at multitask learning and whether it can improve prediction. They also went ahead and so instead of using a built environment feature to predict obesity, they try to just predict obesity directly from Google Street View images. So that was one of their analyses tasks, and it seemed to have gone well. I'm gonna probably maybe exit because it gets pretty sticky. So so I might just do the notes view because I find that the full screen view makes I don't know why the keyboard a little sticky and doesn't like advance forward very well. Let's see. I'm gonna skip down to where we were. But let me know, does anybody have any questions thus far? I'm covering things pretty quickly. Any questions thus far? Okay, I'll go.
Yeah. So good. So far, so good. Thanks.
Okay. Thank you. Okay. So I'll proceed. And they were just predicting obesity at the census tract level. And it seems like the hybrid model predicting obesity directly, also predicting multiple built environment features at the same time seemed to improve the prediction. And then we also leveraged Flickr data. So we learned that manually labeling images can take a substantial amount of time because you have to train your annotators, and then you have to conduct inter-reader reliability. And if that's not good, then you have to retrain it in multiple times, and then they have to label the images. And to get something on the order of like 15,000 labeled images can take a month, if not several months. So the labeling effort is pretty time intensive. So one way to help provide label data is to get it from other data sets. So something like Flickr images is what was used at a later stage for some of the indicators. If Flickr has an abundance of the feature that you're looking for, then it's a possibility to include that into your computer vision model as training data. Here we looked at dilapidated building, chain link fence, and street light. And then we're looking here at the F1 score and accuracy, and it also seems to improve if you use multitask learning. So you're trying to examine them together rather than building separate networks for them. Okay, so I'm going to next get to individual level analyses. So the first paper is looking at these Google Street View derived characteristics predicting patient health in Utah. So Utah is a special state. I'm not sure if you've done research in Utah, but they have massive population data through, for something called the Utah Population Database, which is what we use in addition to Intermountain Healthcare. And Intermountain Healthcare serves along with like University Health Sciences. Together, we had data for over like a third of residents in Utah. Okay. Sorry about the table being small. So we list the individual level characteristics. The only thing about Utah, of course, is that there's for white, it's 95% of our study population was white. But there is a significant representation from Hispanic, with 11% being of Hispanic origin. And then we have the Google Street View features that we examine down at the bottom. So most notable are going to be green streets, not single family home, and visible utility wires. And we looked at their association between those features and chronic condition, as well as substance use disorder. So in summary, we saw green streets and non-single family home having like people who live in communities with the most green streets and the most single family homes had 10 to 26% lower diabetes, uncontrolled diabetes, hypertension, and obesity, controlling for some predisposing characteristics like age, race, ethnicity, religion, marital status, health insurance, and air deprivation. Visible utility wires overhead was also associated with more chronic conditions. So the next series of analyses was using a different healthcare system, University of California in San Francisco. So we did a similar type of analysis with outpatient visits and controlling for some predisposing characteristics like age, marital status, residency, insurance status. Here's what some of the images look like in California, as well as the distribution of the neighborhood characteristics. In California, as you know, there's going to be a little bit more representation from different races. So you have 31% Asian. I'm sorry, not 31%, 18% Asian, about 7% Black, 9% Hispanic. So there's a little bit more racial ethnic distribution representation in California, in San Francisco. And we see pretty robustly still like similar relationships where green streets, visible utility wires are going to be associated with chronic condition. So places with more green streets had 12 to 30% lower prevalence of coronary heart disease, hypertension, diabetes. The presence of visible utility wires was associated with more coronary artery disease and hypertension. Dilapidated building was associated with 9 to 18% higher coronary heart disease, hypertension, and diabetes. And the next and final paper is looking at our largest data set. Here we downloaded 170 million Google Street View images. And Nuplung actually created a geoportal, which is live and you can visit. It allows you to see the distribution of these characteristics across the US, zoom in a certain area, look at the neighborhood features, and download the data. So here it's like the national data set with 170 million images, and then we're looking at the census tract summaries of them. And then we looked at the association between these Google Street View derived characteristics and chronic conditions at the census tract level. And this is on the whole US compared to just like Utah or San Francisco. This is on the entire US. And then we also looked at outcomes like poor mental health days, depression. We generally see that indicators of urban development, for instance, lower urban development indicated by single lane roads, were linked with higher chronic conditions and worse mental health. Walkability and urban ethnicity indicators such as sidewalks, crosswalks, 2 more cars were associated with better health, which is specifically lower obesity, high blood pressure, high cholesterol, and mental distress. Street signs and street walks were and street lights were associated with decreased chronic conditions and mental distress. So the newer indicators were street signs and street lights, and these are kind of indicators of walkability and urban development. So in summary, advantages of Google Street View include its efficiency, researcher safety, because previous neighborhood researchers had to actually visit neighborhoods, so there was some safety concerns depending on the neighborhood. Google Street View is relatively low cost compared to the staffing and travel times that would be needed to do a national study. And the data collection is not obtrusive. Like you're not, you don't go to neighborhoods with clipboards where you kind of would be seen by residents and then do health service residents. So the actual measurement itself might actually interfere with the data results, with the results of your study, in the traditional way of surveys and the more obtrusive on-site visits. But there are significant limitations. So the Google Street View images can be collected at different time periods. There is also a lag in terms of when they're updated, particularly for rural areas. And the view and quality can be limited because some of the images have not the best resolutions and some of the zooms are further away. Also things like parked cars or other things that can block the view of the neighborhood characteristic that you're interested in. And also Google Street View cars cannot drive down unpaved roads. So if you're interested in certain characteristics, but it can't be reached by roads, or at least by Google cars, then it's not accessible from Google Street View images. But I would say there are a host of strengths. So it allows Google Street View images allow for direct extraction of street level built environment characteristics. And leveraging that with computer vision models just enable the neighborhood studies to be much more efficient in larger scales. Also, because each image has associated coordinate, you can pick the neighborhood boundaries that you want. For us, we looked at it neighborhood, like the built environment characteristics at the census tract, at the zip code level, at the county level, even some at the state level. So it depends on just your interest. And also I know certain neighborhood studies will have their own boundaries, and you can just use that boundary because you have image level data. And so you can collapse it in any boundary that you would like. And just through these series of studies, it's demonstrated that Google Street View derived characteristics can be robustly associated with health at the ecological level, so at the county and census tract level, but also at the individual level, because we also examine patient records of individual patient outcomes and controlling for some of their baseline predisposing characteristics. But I would say one of the major limitations of these studies, but as well as neighborhood studies in general, is concern about confounding, especially because neighborhood characteristics are not evenly distributed. And we know that where people live is a reflection of a variety of things. For instance, segregation, their SAS background, their cultural preferences. And so to isolate whether the impact is really the neighborhood characteristic or other characteristics that are correlated with neighborhood characteristics needs to be addressed through tighter control of confounding. So something like sibling studies, as well as longitudinal studies. Actually, in the first study that I mentioned with the Salt Lake data, the very first one with the 3 cities, we actually did siblings. We did a sensitivity analysis controlling, subsetting it to siblings. And we found similar estimates, but they were a little bit attenuated. So that was possible in Utah, but that's not possible for other healthcare systems that don't have family records. But more continued study and tighter control of confounding is needed. And I would take any questions now if you have them. Oh, yes, I had a question already.
Yeah, so thank for give a great talk for introduce how to use Google Street View data to examine the relationship between built environment and the health outcome at different levels, which is pretty cutting-edge methods. So the first question is
Oh, yes.
about the manually label training,
Yes.
the testing data sets in the first project. You mentioned the training data sets consistent with Google Street View images from different cities. I'm wondering, only using Google Street Views of a single city, like Chicago, to train the classifier, will the classifier perform good on predicting Google Street Views of other cities? So in brief, what's your opinion that training a classifier only using one city and repeatedly use it to label the images of other cities?
Okay, yes. So I think that's an incredibly important question and comment. For the first study, we started out using only Chicago, but we actually supplemented it with Charleston data. And that's because Chicago labeled data was fine to label Salt Lake City features, because I think it's similar enough. The way those like crosswalks or green or trees look, it's like similar between Salt Lake and Chicago, but it was not similar enough for Charleston. And so for that, even that study, we had to add images from Charleston to have the model recognize heterogeneity in the features. When we started to move beyond that study and look at national data, there was subsequent rounds of labeling where the labeled images were actually a sample of the US rather than just from one city. So the subsequent rounds of manually labeling were just we take a subset of images from the entire US and use that to produce inferences for the US. So I would say when you're building these models, you want your training data to look as much as possible on your analytic data set. So if the representation is not there, the model would not perform as well when it sees your real data. But then the label data itself is very costly to create. So that's why sometimes people will use already created data, but if that label data does not look similar enough to your real data that you need to like analyze, there's going to be a dip in performance that you should be aware of, and then you might have to supplement. And then I had a raised hand from Chris. Chris, did you have?
Yeah.
Hi, thanks. I can lower my hand. I'm Chris Lucius. I am a landscape architect and urban designer. I teach in the College of Architecture. I think this is really interesting research. I look forward to reading the papers. I'm curious if you considered if there are other physical environment characteristics that you considered and rejected. Kind of the sub question to that is I'm curious if bike lanes or bike infrastructure were ever considered as part of that.
Oh yes, bike lanes are now being considered in this like subsequent phase. We are considering bike lanes more as a so that is being considered. We didn't consider bike lanes yet. I don't know why we didn't. I think it was like more like our focus has now shifted to like transit, where we're going to incorporate more like bus stops, bike lanes, speed bumps, things like of that nature in the new round of analyses that weren't considered yet. But then we can also discuss features that we rejected, not because we weren't interested in them, but because like computer vision models really struggled. So one feature we were really interested in was like litter. So like that's really prevalent in like litter, right? The trash present in a community, but the computer vision model just struggled so much with that because it confused it with leaves that it looked so different that it couldn't really identify accurately. So we like unfortunately had to like it was really sad. We worked on it for several months, but the accuracy wasn't high enough because the litter was looking too much like natural like leaves, and also because it was small in size. So that, and then also graffiti. We tried to do graffiti for a while, but graffiti was kind of a rare feature in our like 170 million image data set that it wasn't like it would be mostly zero. It's like one of those situations where it's mostly zero and then like a drop of the time it's like one. And so the computer vision model just struggles with things that are small in size or rare. So those are some instances where we had to like, it was more complicated than the more low-hanging fruit, the bigger features or the features that looked similar. Even something like dilapidated building, we worked on it for like a year because we really wanted to get it, but it was a very difficult feature because it looks different. When a feature has heterogeneity in its appearance, the computer vision model will struggle with that. Things that look the same, like a crosswalk generally looks the same, then it'll pick it up right away. But if it has any variation that needs to be captured, then it'll be more of a struggle for your computer vision models.
Thank you so much.
So the other question is, could you tell us more about the group that you used to label the images? How were they instructed to perform the labeling? Did they use the same wording and so on?
Oh yes. So this is for when you're doing labeling efforts, I would say it's very important to draw up a data dictionary or like a code book for how to, so everybody's on the same page for how they're going to label. Because initially we were like very informal about it. We're just like, okay, label crosswalks, right? And then not everybody has the same level of experience for what, like, because some crosswalks would look different, and then there would be confusion about whether we should include them. So having a document that describes what the feature is, has example images for what that feature looks like, and then instructs them to say, okay, when you see this feature, put a 1. And if you don't see this feature, put a 0. And then we also played around with like a gradation. So some features have like, it's not just a yes, no, but it could be like a graded, like, dose. And there you're gonna have to also put like how to label the different levels. But our annotators are actually students. And I find that using different levels, like multiple levels, confuse everybody and led to lower accuracies. So in the end, we mainly stuck with dichotomous measures. So I would say one tip is to write up a document for exactly how they should label it and put sample images. And then have a little pilot where they go on and label like 50 or 100 images. Then you calculate the inter-rater reliability. And if it's good enough for that feature, you let them proceed. But if it's bad for certain features, then you have to do a second relabeling effort where you discuss where there are, disagreements or confusion, and then you have a second labeling effort and calculate inter-rater reliability again. But we mainly we had students, research staff on the team that did it rather than having it be crowdsourced, just so that we had like a tighter control of like the training experience and the inter-rater reliability.
I have a question is about for your first paper for the figure 1. I'm wondering, you're showing is the distribution of building environment in Salt Lake.
Yeah.
So I'm wondering, the classification you use is which methods of classifications, because it seems for different paper you use different classification methods. And so how you, I think for your San Francisco that paper you use is a Contel for the classification. So how you actually choose what classification methods you use for the legend symbology?
Oh, you mean the computer vision model or the something else?
The symbology classification methods. So for that figure 1.
I'll figure 1. Okay.
Because it seems you have 1% to 9% is in one category. Then for 1 to 90% is in one category. So that's why I'm wondering which
Figure
1. So the first
1.
paper, figure 1.
Like this one?
Yeah, exactly.
Okay. Oh yeah.
So it seems
yeah, I think that was turd tiles. I don't know. I think that that one might have put it at turd tiles.
This one does not
tile
look
has-
like contails. So this one is yeah, this one is not. It seems your San Francisco, that one is use contails for.
Yeah. I think this was but although there's going to be like the green 30, I think it tried to use turd tiles, but it was like the red and the dark color is bigger. But I think it's mainly turd tile, at least like approximate turd tiles. And then let me go to the UCSF one. This one, 1, 2, 3, 4, 5, 5. So it might be. Oh, and it's here. These are a little bit different because they were holding it at proportions. So it's like 0 to 20. The legend was the same for all features compared to the Salt Lake City, where it was different different percentages corresponding to the different colors. But
Yeah.
Yeah,
it seems because if we use different classification, will be look very different to explain how actually they distributed in terms of the features.
Yeah, yeah. I mean, I think for I think the Salt Lake City analyses, and for I guess a lot of them, we were mainly because the prevalence of these features vary so much, with crosswalks being the most rare feature. So we couldn't really like to say like a 1% increase in crosswalk is different than to say a 1% increase in green streets or a 1% increase in not single family home, just because one thing to take into mind is like the green streets and is much more prevalent. And so like a 1% increase crosswalk is like a bigger magnitude in a way, because crosswalks are generally rarer than the other features. So we mainly looked at turd tiles, and turd tiles will have like varying percentiles, varying like because for crosswalk you don't have to get that high in percentages for you to be in the third and highest turd tile, compared to the other features like green streets or not single family home. here, I guess I will go back to, let's see, here. So we have like just some descriptives of green streets, crosswalks, and not single family home. So for instance, green streets, like it's, it's a very common feature. Like 78% of like census tracts on average are labeled as having green streets, and for crosswalk, it's much more rare. So for Salt Lake and Charleston, you're looking at 3 to 8%. Chicago is higher at 22% of like on average images having crosswalk. Yeah.
Okay, thank you.
Yeah.
So the next question is, I think for different paper, you look at is at different levels. So some is like county level, some is like individual or census tracts. So how you see these different spatial levels actually they interact each other. So for the factors, so
Yes. I would say I prefer the individual level most. So I would prefer like patient data or like individual level health outcomes data, just because it allows me tighter control of confounding, because I control for like their background characteristics as well as the other neighborhood characteristics, not counting Google Street View characteristics. But then a lot of times like patient data is very sensitive and restricted. And so for instance, we only were able to get 2 healthcare systems, and even getting those 2 healthcare systems, it was like sometimes years in the making. Like conversations with Utah, I think 2 years. And then it took like, that long to get data, because this is like, patient data needs to be handled very sensitively and in a, secure way. And then UCSF data, I think it took a year to get, but for both healthcare systems, we sent our neighborhood data, and the analysts at those healthcare systems did the regression for us based upon what we specified that we wanted in the regression models. So one way to finally get those analyses done was to not have the health data leave the healthcare system. So I think that might be a nice tip, because at first we try to like get the data from the healthcare system, but that sort of conversation was very long, and you have to go through both IRB, privacy board, and then the healthcare system was still very worried, of course, what if there was a data breach. So I would recommend like more like when you're working with healthcare systems, you might want to have the analyst at the healthcare system do your regression, but then you're at that point you're limited to major healthcare systems with research infrastructure, because without research infrastructure, the healthcare system will not be able to run the analyses. And then so there's a lot of complexities associated with working with individual level data, but that is my preferred. But at the same when we look at the census tract or zip code level, one of the things it gives you is that more of a national viewpoint, because then you're looking at across the whole US rather than just certain regions or certain neighborhoods. And so you're trying to understand whether these patterns are going to apply to the whole US. But you don't have the same level of like control of confounding, but you have the entire US. You have potentially more generalizability.
So in terms of, you mentioned like complexity, so it's like for the multi-level model will be good to address some of these complexity in your thoughts.
Yes. So in the multi-level model might come in if you're looking at patient level data. So if you have patients clustered into neighborhoods, right? So there you're going to have clustering of their health outcomes at the census tract or zip code or whatever boundary that you pick. There is a way for statistical software and to try to take out the correlation, because one of the assumptions of regression is to assume that your units are independent, right? But if the units are not independent, that they are clustered in neighborhoods, But there's a way to specify that, at least for us, we use just clustered standard errors to tell the models that the units or that individuals are clustered within neighborhoods to try to take that into account. But there's going to be different software that allow for you to adjust or account for correlations, spatial autocorrelations.
Okay, so I think the other question is I'm wondering, like for different project, you use different like algorithm
Yeah.
and the models. So
Yeah.
like some use like a VGG19, some is like a REST and NAT to label the features.
Mhm.
So how you decide for these different algorithm models you use for the
Yeah.
machine learning? Yeah.
Yeah, I think it was we left it to the engineering student. I think they were just trying different models, and they just selected the model that that performed best for that feature, that individual characteristic. So that's why it kind of varies. Yeah, it was just based upon the engineering student and what they when they tested the model, which one they thought would be the best one to run. Yeah, and sometimes that's like VG19, and sometimes it's 16. I think it also depends on like what they were working with, because throughout the life cycle of this project, we had basically a new student every 1 or 2 years. So we had like, students transition in and out. So it's like a mixture of what they were comfortable with, what they were experienced with, whether when they tried different models, which one gave the best results. But I would say even across these different models, it was mainly pretty robust to the model selection. Like it performed reasonably consistently across different models, with some gains if they did some fine tuning or.
So which means that kind of back to the question, I think I just now have a question is asked like how the trade the operator to label this image. So or trade them how to actually run the model. So which means that they are given the certain models, or they just try the different person try different models.
So I would say they mainly try pretty similar. Like there was like it was, I would say most of the papers are written on like models that were done for each indicator. Each indicator had like a model that was built. So there was a model for like green streets, there was a model for chain link fence, visible utility wires. So these were like standalone models that, and sometimes it's there would be a student who took on like some neighborhood features, and then a new student arrived and they took on additional features. So like when the crosswalk feature was done, then we just saved the model and the weights and just reran it when we needed to on new data. But then if we were interested in like visible utility wires, which was a new feature, then a new student would kind of tackle that. But mainly they were still developing pretty much standalone models. And then the later waves started to do multitask learning, Flickr data, incorporating Flickr data, and then to try to do a hybrid approach where they try to directly predict the health outcome from image. So some of those are more like sensitivity analyses that came later on.
Yeah. Also, did you actually do the like sensitivity analysis for these studies?
Oh yeah. I mean, I think there was different sensitivity analyses. Like for instance, the first study we restricted among siblings, and see if that made a difference. Because like then, for instance, like if you had a sibling, then and your sibling live in different places, does the fact that you live in different places help predict the variation in health outcomes? So that was like one sensitivity analysis. And then depending on the topic of the paper, if that was like if an engineering student was writing it, then the sensitivity analyses were mainly different experiments based upon different models that they were putting forth and which model performed best. So, but if it was a public health student, there was mainly like different health outcomes and different neighborhood features and what predicts health outcomes. So it depends on, because we have both engineering students, computer science students, and health students in the project. And they kind of, the focus of their papers were a little bit different flavor. But
Oh,
yeah, so it's like a mixture of both engineering students and health students.
oh, okay.
Mhm.
Yeah, that makes sense. It seems
Yeah.
paper.
That's why it looks so weird. It's like it's like a mixture of both. Yeah.
Yeah, that makes sense. How actually I found the different
Mhm.
papers it looks different for like
Very
especially-
different. Yes.
Yeah, it's especially for like the features choose.
Uh-huh.
Yeah, some actually the features actually choose it seems pretty from the engineering perspective.
Yeah.
Some like those like cross workability or some like
Oh yeah.
green 13 or others. So it's pretty like from the engineering perspective. But some is like health issues. Like I think you also like one paper you use like a child opportunity index.
Oh yes, that's right. Yes. Uh-huh. Social sciences. Yeah.
Yeah. Could you explain how that paper actually use that child opportunity index related to like health outcomes?
Oh yes. So that index was used to more as to control for confounding, because we wanted to understand whether the Google Street View characteristics can predict health above and beyond something as powerful as the child opportunity index or like neighborhood poverty or percent of people with college education in the neighborhood. So we wanted to say like above beyond these really important characteristics, does the Google Street View variables give you any other, like even any other prediction to the health outcomes of interest above beyond like, socioeconomic characteristics or like resource characteristics, which are already closely tied to health outcomes.
I see.
Yeah.
So the other question is like when you do this use this big data to see the to examine the relationship between built environment and the health outcome, did you compare to like traditional data for?
In some studies we did. So the Google Street View project kind of does both traditional and non-traditional methods. So I would say, and also depends on what you think is non-traditional, because I think computer vision is traditional if you were an engineering student, right? But it's traditional if you're a health student. So kind of having both together, you're like, what is it? Like, and also like the health outcomes, like so census tract, county health outcomes all come from the traditional survey. So like places like released by the CDC, so the places data set or BRFSS or NHANES. So all those are really traditional health data set that have geographical identifiers. So that's how we can examine, relationship to Google Street View characteristics and health by using these traditional health surveys. And then we also use census indicators and compare them with Google Street View indicators, like the rural-urban continuum codes or like the population density as a marker of urban development. And we compare it to see if it's like less explanatory power compared to the Google Street View. So we like all the way through, it's like a mixture of both very traditional survey methods, census characteristics, and then Google Street View, which I regard it more as a complement rather than as a like more as additional understanding of the things that can impact health, like the physical features of a neighborhood and how that can affect health.
So which means whenever you build the traditional like a survey, this data is not enough to describe the built environment. So then the Google Street View images can help with the process.
Exactly. Yes.
I see. So I think we already passed the time. Thank you so much for your excellent talk and answers to the questions. So usually we give the applause to the speaker at the end.
Oh, thank you so much.
So, yeah, it's thanks for your talk. So,
Oh, yeah. And please keep in touch if I can be of help to you, or if you had any follow-up questions, feel free to ask.
yeah, I think Quynh leave the her
Yes.
email there, right? Yes.
Yes, I can leave my email. And I'm just like a UMD College Park if you ever need to look me up.